Okay, so the first thing that I want to talk about with you guys is how we know what to do as far as converting from one thing to the next. So let me ask you these questions. In the video, the very first video that you guys had to watch last week, it completed the packet. Did the concept of the mole make sense? Okay, remember, the mole is it's basically a relationship. So if I say 1 dozen, what does that mean? 12. If I say a ring, that's 500. So a mole, by value, is what? 6.02 times 10 to the 23rd power. Okay? Is a ring. Okay? So it's the same exact concept, except it's dealing with chemistry and not dealing with buying eggs. Okay, so that's, or buying a pack of paper. Yes, sir. No. It has to be positive. Yes, it has to be positive. Because think about the difference in the size of that value. Same root, but it's a different exponent. It's a different size exponent, so you go one way versus the other. All right, the second thing that I want to make sure that you guys understood is, does it make sense of when you're given a specific unit, how you convert from one to the other? And the example that I gave you guys was like flying. So if we need to get to New York City, if we drove out to the airport, could we go straight from Dothan right to New York City? No. What's in the middle? Atlanta. My brother's job makes him fly a lot, and people say, well, do you like flying out of Dothan? He said, I can get anywhere in the world from Dothan. They kind of look at him and he said, no, you can't. He said, yeah, I can. 30-minute flight to Atlanta, and I literally can go anywhere in the entire world. And he's kind of telling the truth. It just takes that flight. So in this concept, what I related Dothan to is grams. Okay? And it's arbitrary. I just kind of made it up to apply it to something. All right, in Atlanta, I made my moles, and then in New York City, I referred to it atoms and molecules. Now, I need to pause and focus on that part of it for just a second. Is there a difference between an atom and a molecule? Yes. In the video, it kind of went through it. What are atoms? One single thing. So here's how you do it. If you can match the symbol to a box on the periodic table, it's an atom. Okay? If you can't match the symbol to a box, it's a molecule. So prime example. And again, I'm just going to... So H versus H2. Which one of those match a box on the periodic table? H. This is one single thing, so this is an atom. Now, this is just 2 hydrogen atoms, right? But when you take those 2 hydrogen atoms and you put them together, what does it create? It creates a molecule. So that is the difference. So if it matches the box up there, then you're going to call it an atom. There's no difference in what you do. It's just how you label it. So that's going to be your only difference. Okay. So going back to this, I'm going to start with an easy one. And this is for this time in your chemistry path, that if you ever see moles, what did you put beside it? A 1. I cannot stress to you how important that is. So anytime you see that word, give it a 1. Now, we're going to adjust that a little later on in the year, but for today and today only, don't think anything else more complicated than that. So then we have to add this concept. Well, if I'm going from grams to moles, what do I have to use in order to figure that out? If I need grams, where does it come from? Very good, the periodic table. Now, one of the things we talked about in the video was, and I want to make sure that everybody caught this, there's a unit for grams, for the molar mass on the periodic table. What was the unit for the molar mass on the periodic table? Grams per what? Mole. Very good. And this is going to come into play in just a little bit. We'll come back to this. Okay? Now, what if we have moles and atoms, or moles and molecules? There's another thing we have to use. What do we use on this side? Avogadro's number. I know avocado just wants to blurt right out of your mouth, doesn't it? It happens, okay? But it is Avogadro's number. And so, again, that number is very important. 6.02 times 10 to what power? 23rd. Okay, so that's the number that I need you to have memorized. So let's go ahead and let's look at our first problem. And again, if you've done this, awesome. If you haven't, you can just do it again. So the first problem says 9.03 times 10 to the... matter of fact, I want to do this instead. Let's scroll down and let's look at number 3. There's a reason why I'm doing this. These are a little bit easier to begin with. Okay, so number 3 says, please convert these measurements into moles. So we're starting with 56.7 grams of carbon. Now, simple question, is carbon an atom or a molecule? It's an atom because it's one single thing that you can match up there to the wall. So here's what we're going to do. We're going to set this up with a set of parentheses. Now, what unit have we been given? Grams. Okay? So if I need to get rid of grams because it says please convert these things into moles, if I want to get rid of grams, where should I put it in this setup? On the bottom. Okay? But here is the most fundamentally important question, and I'm going to come back to this. According to this thing, now that I've gotten a bunch of junk written all over it, can you go from grams to moles in one step? Yes. You can go from Dothan to Atlanta in one step. So coming back to this, I know that this is possible. Okay, I can go from grams to moles in one step. All right, so let's do the next part. The first one that's the easiest is moles. Anytime you see mole, automatically, what do you write down beside it? A 1. And this one's going to be just as easy because it's not very complicated. But I want to make sure that we're understanding the concept here. Is the grams, the mass. Where do you get the mass from? Periodic table. Okay. But here's the good news about this one. Is there one box with the letter C in it? So can you get just that number and plug it in? Does anyone know the mass of carbon? Very good. 12.01. Now, I want to say this out loud. And again, we're going to come to it in just a second. But the one below it where it says CO2, and I know you heard this, is there one box on that wall that has CO2 together? One box. No, and that's how you're going to calculate the molar mass. And I'm going to show you that in just a minute, so we'll do it together. But I just want to make sure that you kind of understand where these numbers are coming from. So now in our calculator, what are we going to do with those two numbers? Divide. Very good. So let's pull this up. Help me out. What is it? What's the number behind it that I can't see? 56.7 divided by 12.01. Okay? So there's your answer. Now, up until this point, and again, I know you heard this on the video, but I'm saying it live to you for the first time. Up until this point, whenever you wrote an answer, you had two things you had to worry about. First was the significant figures. Second was your unit. Today and henceforth, which means forevermore, there's a third thing you have to tell me. What is that third thing? The substance or the symbol. You've got to tell me what you're working with. Because when we get this, is moles of carbon completely different than moles of sodium? They're all different. So you have to be specific of what it is. Now, looking at the given, it's 56.7. So how many significant figures is that? 3. And let's come back over here and look. We've got, what will we round that to? Okay, very good. So we've got 4.72, and it's moles of carbon. Now, in the video of the very last part of the note packet where it talks about moles, there were 5 Petri dishes. Do y'all remember that? I actually want to show you. Okay. What was the one thing that all of these 6 Petri dishes have in common? How many moles? 1. Okay. All 5 of those contain, excuse me. So when you all hear that they're 1 mole, what would you assume that they would look like visually to your eyes if it's all 1? You would assume they would all look the same. But this proves what? That 1 mole of anything is different from everything. Let me say that again. 1 mole of anything is different than what? Everything else. So if I can compare any of these things, they're all going to be different, even though they're 1 mole. Okay? And let me explain why that's true. Let's look at this top one. This is iron 3 chloride. So the chemical formula for this would be FeCl3. Okay, well, let's look over here. We've got potassium iodide, Ki. Which one of those two things looks more? Like, well, you have more of it. Not even talking about blue. Okay, the FeCl3. It looks like it's a lot more. Okay, and if you look at the mass, it says it's 270 versus 166. Well, if you compare those two numbers, well, that's logically true, right? 270 is way more than 166, so it should be more. But again, what do they both have in common? They're both 1 mole. So why does one look like more? Why does one weigh more? And here's why. You've got iron and chlorine and potassium and iodine. Those are 4 different atoms. Do you agree? Do all of those atoms weigh the same? No. That's why. And are all 4 of those atoms different sizes? Yes. So since they're different sizes, they take up more space, or they take up less space. And so that's why they have different sizes. So they look like they're more. They weigh a little more because the atoms are all different, even though, again, one last time, what do all 6 of these all have in common? They're 1 mole. So if you ask me, all right, that's 1 mole of something, what does it look like? Is it easy to describe that? No, because 1 mole of anything looks different from everything. So you can't make it all look the same. So what does it depend on? It depends on what the substance is. Okay? That's the key component in this, is that visually doesn't matter. The moles are going to look a little bit different from each other because their masses and sizes are different. All right, so let's do the next one. Let's go down and let's do C. Now, this is going to be fairly simple. As a matter of fact, let's just do B because I don't want to do C. Let's do this one. So we've got 5.67 grams of NF3. Now, just like with the last problem, I want to get rid of grams and I want to get into moles. So if I want to cancel grams, where do I put it? Put it on the bottom. And can I go from grams to moles in one step? Yes. So the easy part. You see moles, what do you put beside it? A 1. Very good. So here's the tricky part. Is there one box with NF3 in it? There's not. Okay, so that's a compound. That's a molecule. So we've got to figure out what the mass of this thing is. So I'm going to come off to this, and I'm going to be 100% honest with you guys. I want you all to get to the point where you do not have to do what we're fixing to do. I don't want you to have to write it down. It takes too much time. It gets aggravating after a while. So I want you to progress to the point where you can do this in your calculator. Definitely not in your head. That's impossible for me anyway. Some of you may can do it in your head. But the math can get too complex for some of these things. So I want you to begin practicing on how you can make this more efficient for yourself. So let me just go ahead and set it up. Remember what we do is we label each atom and we determine how many of each are present. So how many nitrogen atoms are in NF3? 1. All right, how many fluorine atoms? There are 3. Okay. And then what we're going to do is we're going to use the periodic table. We're going to find out how much each one weighs. Anybody know the mass of nitrogen? Very good, 14.01. Now, and I may have said this in the video and I can't remember, so I'm going to say it to you again live. When you're on the periodic table, when you're looking at those masses, and again, you're going to get these little yellow ones, okay? How many decimal places do you round those numbers to? 2. Always round to 2 decimal places. Now, am I going to be mean and rude and jerk about it? No, not for the first few months. When we get to the end of the year, I may be a little rude about it, okay? Always round to 2 decimal places. All right, so does anyone know the mass of fluorine? 19 even. Very good. And the reason why is it's actually 18.998. Well, if you round to 2 decimal places, that kicks it up to 19. And again, I could be wrong. I'm saying with a disclaimer I could be wrong. I think there are only 3 elements on the entire periodic table that when you round it goes to whole even numbers. One of them is oxygen at 16. One of them is fluorine at 19. One of them is chromium at 52. As my memory serves, I think those are the only 3 that you can round the whole numbers like this. Okay. So now, what do we do with these numbers? Multiply, and what do you do then? Add it up. So, again, this takes a while if you have to stop and write it down and think about it and then plug it all in. If you can just learn how to look at the periodic table and do it all in your calculator, it goes so much faster. Does anybody have the mass of this thing? 71.01. Okay. All right. Now, the last part. And this is, I've already mentioned this, but I want to say it emphatically again. What is the unit on this thing? Gram per mole. Let's completely take chemistry out of context for a second. Let me ask you a real life question. When someone says that car is traveling so many, and make up the number, miles per hour, what does that unit really mean? Okay, when you say every hour, how many hours? 1. So for every 1 hour, it's how many miles you can travel, right? So if you are driving 60 miles per hour, how many miles can you go in 1 hour? 60. Does that make sense? We know that because that's easy common sense stuff we deal with every single day. But when you look at this, all of a sudden your brain turns into mush and you don't understand. When it's identical concept. So when you say miles per hour, that's how many miles in every 1 hour. Well, when we say grams per mole, what do we mean? So for every 1 mole, there's that many grams. That's exactly what this means. So if I have 1 mole of this stuff, it weighs 71 grams. That's the key part here that I want you to get in. This is why it should make sense. When we come back to this, look at your setup over there. What is similar but dissimilar about exactly what we just wrote? Inside the parentheses, it's just upside down. Okay? So if I come in here and I write 71.01, could you still read that as 71 grams in 1 mole? That is the molar mass ratio. You're just putting it in a set of parentheses. Now, mathematically, why do we have to set it up this way? Perfect. That's exactly right, Grayson. Say that one more time. We need to cancel those grams. Because if you did it the other way, would it mathematically be correct? No, you get the wrong answer. Okay? So you should hopefully see the relationship here of what we're doing. Is we're just using parentheses to help our math out. But all we're doing is we are establishing a relationship for the molar mass. So you good? Okay, I just didn't know if you were. So, when we do the math here, we've got, that's the wrong button. There we go. On, clear. Erase this so we can see it a little bit better. We've got 5.67 divided by 71.01, and there's your answer. Okay. So look at your given. Your given is 5.67, so we need 3 significant figures, which is going to turn out to be what? 0.0798. 0.0798. That's 3 significant figures. Remember that first 0 doesn't count. And then what would you have to add behind it? Moles of NF3. Any questions on that? Okay. So we've done 2 examples like that. Let's go back up and now let's look at let's go back up to number 2. So 2A. So this time, we're going to convert these measurements into atoms. And again, this is really or molecules. Now, I'm going to be 100% honest with you. I don't even know if you guys noticed it. In the at the end of this question, it says, in the parentheses, it says apostrophe cules is an unofficial abbreviation for molecules. I'm 100% okay if you do that. Like, in fact, that's how I always do it. So if you want to write cules, that is 100% acceptable. In fact, it's encouraged. All right. So my first question is, we've got 3.5 moles of K. What is K, first of all? Potassium. Is potassium an atom or a molecule? It's an atom, so it matches up here. So your answer is going to be in atoms. So let's set it up how we know what we're doing. We know we need to get rid of moles, so where do we put it? On the bottom. And here's an all-important question. Yes, ma'am. I do. Sounds good. Thank you. Okay. So here's the question. We're starting at what point? What city are we starting in? No. Atlanta. We're starting in Atlanta. Okay. Can you get to New York City in one step? Yeah. So we can go from moles to atoms in one step. But what's the key thing that's between moles and atoms? Avogadro's number. Very good. So we come over here. We know that we can go from moles to atoms. These problems to me, this is just kind of me speaking out loud, as far as setup are easier. As far as calculation are more challenging. And let me explain why they're a little more challenging. First of all, if you have moles, what do you always put beside it? A 1. Whenever you have atoms or molecules, what do you always put? 6.02 times 10 to the 23rd. I have faith and confidence in every single one of you to be able to do this part of it. Every year there are 2 mistakes that I see. And remember, I've been doing this long enough now to know to tell you where you are going to mess up if you make a mistake. I have confidence in this part. Most people get this part right. Putting this in the calculator is the first mistake that students make. They don't know their calculator well enough to put this information in. Okay? So I'm begging you guys to learn your calculators. Help me out. What was that number? 3.5? Right? Okay, so 3.5 times 6.02. And this is the part that a lot of you kind of not sure of what you're supposed to do. In my calculator, I know mine, I have to hit second and then hit that EE, that blue EE button. Some of you don't have to hit second. Some of you do. This is where you have to know your calculator. And then you're going to put in 23. This is the first mistake, is actually physically plugging these numbers in and getting the right answer. Okay? It's times 10 to the. The E represents, that's a good question. So in my calculator, the button is EE. The display, that was not good, is E. But the what it represents is that. So again, it's you learning your calculator. The button is the EE button for most of you. I've also seen this button, X10, and there's like a little dotted box or something. I don't know if y'all have that one. Hold up your calculators for me real quick. Yep, Chloe, the one that Chloe's got, Jack's got. Some of y'all have that little button at the bottom. But again, it's you knowing your calculator. Sir. You could not. And the reason why, and this is why I'm saying that you can't just put times 10. Grayson, what that's going to do is you're going to be off by 10th place on either side. And that's the problem, is if you because really you're multiplying it times 10 and then raising it to the power. Does that make sense? So you're moving the decimal and then raising it. So that's why it's kind of weird. So it's all about learning your calculator and how to do this. So this is the answer you should have gotten. So I've told you mistake number 1 is physically putting the number in. Mistake number 2 that I see. Now this one's not as hard because the number's kind of short. But students will miss that part. Real quick, let me say this out loud. What they put is 2.11 and stop. They forget to raise it to the 24th power. So they leave off the exponential notation. Okay?